Hey, this is Mr. Ainsworth, and we are going to get into my 7th lesson on exponential functions here, dealing with a growth situation. So let's take a look at it here. This is a cool one. It's about cell phone subscribers here. And you guys should know about cell phones because you use them every day. So let's get right into it. Let's read the problem first as I organize the screen here. So here we go. In 1985, this is back when I graduated high school, so a long time ago, there were 285 cell phone subscribers in a small town of Centerville. The number of subscribers increased 75% per year. That's obviously important, so let's highlight that. It increased 75% per year after 1985. The big question is how many cell phone subscribers were there in Centerville in 1994? We're talking about this year right here. All right, so what we're going to do is we're going to calculate them first. All right, so initially in 1985, we're talking about the starting year here, which we're going to call x equals 0, the starting year. There were 285 users, all right, so subscribers, if you will. All right, the question is how many right here, how many were there in 1994? That is right here. The question is, I don't know. We got to figure that out. But we do know that it's increased by 70% per year. All right, that means after year 1 year later in 1996, or 86, excuse me, all right, there was a 75% increase. So that means that from year 1985 to 1986, there was a 75% increase. So instead of having just 100% of what you have, which is 285, it had 100% right here from here to here, 100% plus 75% more. Well, you guessed it, that's 175% of the total. So let's write that down. So in 1986, there's 175% of the starting number of cell phone subscribers in 1985. So the question is, what's 175% of 285? Well, what you have to remember, that 175%, let's do it off to the side, all right, means 175 per 100. Percent means per 100. In fact, let me write that down. All right, percent means per 100. All right, so if I want to convert 175% to a fraction, I go 175 per 100, and as a decimal, well, you can shift the decimal place 2 times to the left and get 1.75, or you can learn from your calculator and learn from grade school is that we take 175 divided by 100, the decimal shifts 2 places to the left, and you get a 1.75. All right, so 175% is 1.75 as a decimal. I'm going to put that down right here, 1.75. So what we need to do is calculate 175% of 285. You want to multiply by 1.75. Let me put that in red. All right, so from here to here, I'm going to multiply times 1.75. And what do we get? Well, let's do that on the calculator. We get to use the calculator to our advantage. So let's learn how to use it in all kinds of situations here. So 285, let me clear it out so you can see better here. 285 times 175%, which is 1.75, is 498.75. All right, so roughly, well, you got to round up, so about 499. So let's put that in there. So 499, so 499 users. It's increased. Obviously, it went up. It starts at 285, but every year it increases 75%, so obviously this value goes up. The easiest way to calculate that is to take 175% of the previous year, which is 285. Once more, you got to multiply by that to get to the next year. So to get to 1987, because it says per year here, okay, read the language, you do the same thing. You have to calculate, 175% of the previous year. So you got to multiply by 1.75 again. All right, that's what you got to do. To get to the next year, you got to keep on multiplying by 175%, which as a decimal is 1.75. All right, so to do that, you just go times 1.75, and in 1987, there's 873, roughly 873 cell phone subscribers. So let's put that in, 873. And you keep on doing that, times 1.75. And you figure out how many cell phone subscribers there are for each year if it increases 75% per year. So now we have 1,500, roughly 27. So 1,527 subscribers. And again, multiply by 1.75 to get to the next year, times 1.75. Every time you do that. So you just go times 1.75, which is 175%. You get about 2,673 now. So 2,673. Let me check that value. There we go. All right. Now in 1990, it has 175% more, right? Or excuse me, 75% more for a total of 175%. So times 1.75. 4,678. All right, so keep on doing this. Go ahead and complete the table. All right, just work ahead of me. All right, just keep on multiplying by 1.75. So, and then you can figure this out. And you keep on doing this. So 8,186. All right, again, times by 1.75. Just keep on doing it, man. It's that simple. So times 1.75, and you get 14,325. 14,325. You know, it's growing, so the numbers keep on growing here. The question is this linear or exponential? We'll talk about that in a minute. All right, once more, multiply by 1.75 and see what happens. So times 1.75, you get 25,070. So 25,070 cell phone subscribers. Notice how I'm rounding it to the nearest whole number, because we're talking about subscribers, and there can't be a fraction of a person here. See, this is whole numbers only here. Whole numbers only. Doesn't make sense to have a fraction of a subscriber. I've never seen that happen in AT&T, Verizon, or Sprint, or T-Mobile, any of those. All right, times 1.75 again, because we're trying to get to 1994. So here we go. In 1994, there are 43,872. 43,872 subscribers. It's a comma. All right, so there's my answer to my question right there. So my conclusion right now is let's put this in blue so it stands out, is 43,872 subscribers. Subscribers in 1994. That's my conclusion. I'm talking about my conclusion right there. So I figured it out the long way, okay, and that's how you would do it by hand if you didn't know about exponential functions. However, you know, I wouldn't do it that way. I would do it a different way. All right, I know that a growth function, like from my previous lesson here, and so let's go back in time too, just to bring you back to the past, is always represented by this function here. The future value, a of f, is equal to my initial value times some base. Now, if it's growth, it's 1 plus r. If it's decay, it's 1 minus r, where the base is less than 1. Or if the base is bigger than 1, it's a growth. Okay, so this situation here, the interest rate is, or not interest rate, the amount of increase is 75%, which is 0.75 as a decimal. So I know the growth rate in this case, let's just go with the flow here, the growth rate is 75%. That's the growth rate. So it's 75%, and as a decimal, it's 0.75. Once again, do it on your calculator. 75 divided by 100 is 0.75. The initial amount before the growth began is right here. That's the initial amount. Take good notes, okay? Go ahead and label everything. That's your A right here. A equals the initial amount. All right. R equals the amount of, or your growth rate as a decimal or a percentage. All right. But when you substitute in here, it's a decimal. X is the number of years since 1985. All right, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 years since 1985. All right, so x here is going to be equal to 9 here in a minute. So if I wanted to really do this using an exponential function here, I could do that. I can say y, the future amount, okay, y equals future amount. Let me just note that. Future amount, all right, is equal to the initial amount, which is 285, all right, times 1 plus the growth rate, which is 0.75, to the power of 9, because it's 9 years since 1985. All right, 9 years. And we can figure that out. Now, this is 285 times the quantity of 1.75 raised to the 9th power. Let's see if we get the same value here. So let's bring the calculator back. Let's take 285 times the quantity of 1.75 raised to the 9th power. And I hope to God it's the same. And it is. You compare the values right here. So let's capture that screen image right here. All right. Gotta love this technology here. And you can just take what you need and clip it on in here. Give me a second here. There we go. All right, so there we go. So that's what the calculator was giving us right here. Notice that whether I do it by hand right here and generate 175% of the previous year and do it with consecutive years, one after another, all the way to the end goal, or I use my exponential function here, I get the same value. I want you to compare these numbers here. Look, they're the same. One's doing it the long way, year by year, and the other one's using our exponential function. Also, there's a third way we can do this here. Let's suppose you don't know this exponential function. There is what's called exponential regression. So what we're going to do is create a scatter plot, and like we did with linear regression, but this doesn't end up being in a straight line here. So I'm going to show you that it actually resembles an exponential function, and you can actually do it on your T84. So what we're going to do is we're going to label this or put these values in list 1, and we're going to label these values in list 2. We're going to use the starting value of 0 instead of these 4-digit years. I'm going to just use the x values here, and I'm talking about these right through here for our x lists. And our y list, we're going to use obviously the number of cell phone users. So what we're going to do is we're going to do this on the calculator now. Check this out. Go to stat mode. We're going to edit a list here. So we're going to select 1. We're going to go up to the top and clear it out. Don't press delete. All right, you'll clear the list, and then you have to reset your calculator. Use the clear button and go down. That clears the list. Go back to L1 and enter in 0 through 9. So 0, enter 1, enter 2, enter 3, enter 4, enter 5, enter. Keep going all the way up to 9. All right. Now go back up to the top and enter in your cell phone subscribers, 285. All right, and then 499. Put your left finger on your numbers on your left, if you're left-handed, and then type them in with your right hand, and keep track of what you put in. All right, 873, 1527, 2673, 4678. And you got to get these numbers right, otherwise it won't come out right. So 81, 86. Got to be careful how you enter the data in. So 7, 14,325. 8, 25,070. So 25,070. And then last one, 43,872. So 43,872. All right, we're good to go. Now we want to go to y equals here. Turn your plot on. All right, and we want to select zoom number 9, I think, zoom fit, or actually zoom stat. We'll try either 9 or 10. I'm going to zoom. Let's go zoom fit. Let's try see what happens. Okay, enter here. I'm going to try that again. Zoom 9. Okay, everybody select zoom standard. Zoom Zoom stat, there we go. Select zoom stat. Let me write that down. So make sure that when you enter the data in zoom stat number 9, zoom number 9, all right, for zoom stat. Make sure you do that so you can see all the plot points. Okay, so that's what I did there. Notice when I can see the graph right now. The question is, you know, what kind of function models that data? And it's definitely not linear because it's not straight. All right, so we don't use linear regression, but we notice that they really take off fast up top here. As x increases, so does y, and it really curves up high quickly. So what we're going to do is we're going to see if the exponential function would work. So what we're going to do is we're going to go hit stat. It's a calc. And notice what we did before. We did number 4 last time for linear regression because the data was linear back in the previous units, but this is clearly not. So we're not going to select 4, not even quadratic regression, that's second degree, not even cubic or quartic. Let's go down. Let's see if we have exponential regression here. Okay, natural log regression, exponential regression. Here we go. It's EXP. So we're going to select number 0, hit enter there. We have to go back into stat mode, and we have to, God, I got to recall this. Let me see. Calc, no, we have to go, oh, we have to recall them, so hang on. Let me go back. Let me think here. Let me think. So second list. Yeah, there we go. So names, we're going to call L1 right there, comma. All right, L2. So go second. Go down to L2 here because our y values are in L2, and we want to see the function. So what we want to do is go vars, y vars, function, y1. There we go. Well, I think we're going to need a comma in there, comma y1. So comma stat. Excuse me, vars, y vars. Sorry, it's been a while since I've done this. Number 1. There we go. Y1. There we go. So we got to separate everything with commas. All right, hit enter. And we get our exponential function here. Notice that A right here, our coefficient is 285, which corresponds to this right here. A is 285. That corresponds with a coefficient 1.749 is the same as 1.75. And when R is 0.9999, that means R equals 1. That means 100% correlation, which means the data really corresponds, I mean exactly corresponds with, our function corresponds with the data here. It's an exponential regression. Okay, so let's go ahead and get that. Let me bring that right here. Clip that in. Sorry, it took me a while to get because I haven't done this in a while, but I got it. All right, so let me paste this right in here so you can see it a little bit better. There we go. All right, so this is my function here. So A, our function, exponential function is right here. Our value for A is about 285, just round it. So this gives me right here y is equal to 285 times b, the base, okay? Remember, it's always y equals a times b to the x. All right, b, the base here is 1.75, which corresponds to what I said earlier, raised to the x power here. That's my exponential function. And this, my friends, is the same thing. This function here is the same thing as what I have up here. So in general, any growth function here is a times 1 plus r to the x power. It can be found by taking your data, substituting them into your calculator here, going and making a scatter plot, doing exponential regression. This is an exponential regression line right here, or curve, actually, an exponential regression curve. In fact, let me write that down. This is an exponential regression curve, all right, and it models the data. perfectly well, because right here, when R right here, let me repeat what I said earlier. When R is 0.9999, which means that R is equal to 1 basically, that means it's 100% correlation. It's 100% correlation, which means that the data models the function exactly correct. All right, and that's a good thing. Okay, that's what you want. It's not close. All right, this function is not close to it. It exactly models it. Okay, and then what you do is you just graph the data here and take a look at what it looks like. All right, you're going to obviously have to change the scale right here because the biggest Y value is 43,000, roughly 45,000. The biggest X value from 0 to 9, okay, that's easy. So 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9. The question is, what's your scale going to be here? Because you have to count all the way up to 45,000. So let me see, it's got to be huge, right? So 5,000, 10, 15,000, 20. So let's count by 5,000. So 5,000 here, 10,000, and we got 20,000 here. Probably make it 25,000. All right, 30,000, 35,000, and 40,000, and 45,000 here. So if you change the scale, all right, then you can plot the data, and you can see what this thing looks like. All right, so let's go ahead and do that, because that's something that you need to be able to do. Let me zoom out so I can see the points here. There we go. All right. And so you're going to have to estimate, obviously. So these are the years right here. All right, and this is the number of cell phone subscribers. So you just go ahead and plot. So let's go ahead and do that. So at x equals 0, which is the y-intercept here, you get 285, and that's barely above the axis here, because this is 0 to 5,000. So you estimate. At x equals 1, we have roughly 500, which is just a teeny bit above it. 2,873, which is just a teeny bit above that. 3,1500, just a little bit above that. 4,2673, which is halfway between 0 and 5,000, right about here, perhaps, right about there. So it's increasing here. At 4,700, 4,700 is a little bit under 5,000. 6,8200, so you go up about 8,200, a little under 10,000. 7,14,000, so you go up about, let me see, that's 15, 14 is right underneath it. 8,25,000, right about there. And 9,43,000, right about there. So if you graph this function, it looks like it's a exponential, and it's increasing quickly. I mean, every year it's increasing by 75%. Let me clean this up a little bit here. There you go. All right, so it's increasing. It's a growth function. All right, so you can see that a little bit better here. Dun, 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 and that cool technology. All right, there you go. So estimate the points. Estimate the points, the position or the points. All right, and graph them all, and you can see that it's a growth curve. Growth curve. It has to be. Everything's increasing every year by 75%. All right. Boy, I put a lot together there. There's a big example of how to use technology and how to determine the function of a situation where you're increasing by a fixed percentage every year, per year. This is obviously important right here. You can always use this growth function there. All right? All right. Well, that's it. This is Mr. Ainsworth. I'm signing off, and I'll see you in my next video or in your next lesson. See you then.